first example is a basic jump function. So just for the sake of remembering the situation, the absolute value of x over x, that function has a jump at 0 because it's completely definitely undefined at 0. And on one side it'll be positive 1, and on the other side it will be negative 1. Then when you start shifting and so on and so forth, this one shifts left 2 units. So the jump is happening at negative 2. So we've just shifted this graph over to the left 2 units to become this. And so at negative 2, there's a jump. So the limit as you approach negative 2 is non-existent. I want to explore 2 and 3 a little bit more in depth, okay? 2 asks for the limit as we approach 0 from the left. Let's think about what is the divide that's happening at 0. Likely some jump because we have an absolute value here. What if we are plugging in positive numbers? What is always going to happen if you're plugging into this function, if you're plugging in a positive number? If I plug in a positive number, what's happening? Always, no matter what. 0. Because the absolute values make no difference if x is positive. So if x is positive anyway, this might as well be 1 over x minus 1 over x. So it's always 0. So to the right of 0, this function is just a flat line at 0. At 0, it's quite obviously undefined. But let's look at what happens to the left of 0. So if I were to plug in, let's say, a negative 1, my y coordinate would be 1 over negative 1 is negative 1 minus, if I were plugging in a negative 1, the absolute value of negative 1 would be 1, and 1 over 1 would be 1. So that would be overall negative 2. What if I plug in a negative 2? This would be negative 1/2 minus, what would that be? What's 1 over the absolute value of negative 2? So the absolute value of negative 2 is 2. So this would just be minus 1/2. So what would that be? Negative 1/2 minus 1/2. Calculus always does tricky things with simple numbers to us too. All of a sudden we can't think about 1 plus 1 anymore when we're doing calculus. That's a real disease. What's that?
1 plus 1 can equal 5.
I know. Your mind does silly things to you because you're so deep in thought that 1 plus 1 all of a sudden is like an astronomical question. So I'm just going to sketch these. Negative 1 is at negative 2. Negative 2 is at negative 1. What's going to happen at negative 3? If we plug in negative 3, we get negative 1/3. Minus, if I plug in negative 3, the absolute value becomes just 3, so it's just minus 1/3. What's that? Negative 2/3. Negative 3 is negative 2/3. So what do you think, as I keep going towards negative infinity, what seems to be happening? It looks like it's approaching 0. We can just confirm with one more. That would be negative 1/4 minus 1/4, which is negative 1/2, which gets even smaller. So I think that's fair. But what's going to happen as we keep approaching 0? So we already plugged in negative 1. Let's plug in negative 1/2. What is 1 divided by negative 1/2? Negative 2 minus, when I plug in negative 1/2 here, the absolute value of negative 1/2 is a positive 1/2. And what's 1 divided by 1/2? 2. So it's minus 2. So what's that? Negative 4. So So negative a half is negative 4. Let's do negative a fourth. We'll get even closer. What's 1 divided by negative a fourth? Negative 4 minus. Now when you plug in negative a fourth to the absolute value signs, it becomes positive a fourth. And 1 divided by a fourth is 4. So negative 4 minus 4 is negative 8. So if I go to negative fourth, I'm at negative 8. So what's happening as we approach 0 from the left? Negative infinity, which would be b, non-existent. Okay? Any questions on that? If you just look for the overall limit, like it's a little, it takes more exploration here because we're talking about approaching 0 from the left specifically. We should know right off the bat that the limit as you approach 0, without coming at it from a specific side, the limit as you approach 0 is definitely not going to exist because you can directly evaluate that and you would get 1 over 0 minus 1 over 0, which is undefined. And so you know that the limit doesn't exist overall, but you're not sure, is it because of a jump? And so maybe the limit from the left exists and the limit from the right exists and they just don't match. But the reality is the limit from the right here does exist. What is the limit as you approach 0 from the right? 0. But obviously as you approach from the left, we've seen with the pattern that does not exist. So sometimes, and when I asked Mrs. Hill about this with some of the trickier absolute value ones, she says that she almost always with absolute values just tries to like play with the graph. Just graph it. Now, just graph it with absolute values, it's not that simple. Like just graph it. Like that makes it sound like it's easy. There's a lot of exploration that has to happen. At the very least, these parent functions, that's easy to graph, or should start to become easier to graph as you become more familiar with that parent graph that we did, I guess, last week some point, and the shifts and stuff. But when it's not of the parent graph form, like number 2 wasn't, you just literally have to sit there and explore it, knowing that something funky is definitely happening at 0. It's got absolute values around it, and it's in your denominator. Would you ever try, and I'm just brainstorming here, I have no idea if it's going to lead me anywhere, but like getting a common denominator? Or would that just be ugly? Like if I tried to get a common denominator, this would need the absolute value of x. It's too weird. This one would need just the plain x, and then it would be over x absolute value of x. I think if you split it up, you're just going to be back to where you were. That's what we just undid, was the split up, right? Yeah, I don't know that coming at it from that vantage point gives us any additional understanding. Kind of a dead end. Okay, number 3. I want to explore 3 because, number 1, we have the square root of x squared in the denominator. So this can be simplified to what? X squared over absolute value of x. Now, something funky is definitely happening at 0. Number 1, it's undefined. Number 2, it's got absolute values, so it makes me think that there might be some sort of jump happening. What happens to the right of 0? Like if we were to plug in 1, what would we get? 1 over 1. What if we plugged in 2? 2 would give us 2. What if we plugged in 3. Right. Because when you plug in a positive number, the absolute values really aren't doing anything. And you can reduce, obviously, x squared over x to just being x. So it makes sense that when we plug in 1, we get 1. So if we're moving to the right, this looks like that. And then we want to explore what happens on the left side of things. So what happens if I plug in -1? I get 1 over 1 is 1. What happens if I plug in -2? No. I get 4 over 2, which is 2. What happens if, so I see -1 is at 1, -2 is at 2, so it kind of looks like a similar thing is happening, but let's get closer to 0. What if I plug in -1/2? That's going to give me a 4th up top divided by a 1/2 on the bottom. What's 1/4 divided by 1/2? Keep, change, flip, 1/2. So you can see the pattern remains, doesn't it? And we get, so is there a jump? No. There was obviously the potential for a jump, but after further exploration, we see that this is a removable discontinuity. And the limit as you approach 0 does exist. It is 0. So cases where the absolute value makes us have to explore quite a bit more. Josh. On really, really tricky ones. You know, that it's not efficient. Manipulation's always better if you can, but sometimes it's just not in the cards. What if I did this? And I'm just playing. I don't know where it's going to lead me, so you don't feel like you have to write this down. But what if I split this up into x times x over the absolute value of x? And using our properties, we should be able to take the limit as x approaches 0 of x and then multiply it by the limit as x approaches 0 of x over x. Now we should know that this is what? Does not exist. Times 0. So this, if you think about it from that vantage point, is one of those indeterminate cases. Okay? Where 0 times does not exist is still the indeterminate case, which coincidentally here happened to be 0. But that's not because 0 times anything is 0. You follow? Okay. All right. Other ones I wanted to look at. Number 9. 9 through 13, really. All right, so on 9, we're approaching 0 from the right. So let's just start plugging things in. What happens if you plug in 1? You get a 1/2. What if you plug in 2? A 1/2. What if you plug in 3? 3 over 3 plus 3 is 3 over 6, a 1/2. What if you, so let's get closer to 0 then. Let's go 1/2. What if you plug in a 1/2? You get a 1/2 divided by a 1/2 plus a 1/2. What's a 1/2 plus a 1/2? 1. What's a 1/2 divided by 1? So guess what's happening as we approach 0 from the right? It's always going to be a 1/2. So that's your answer. That's your limit. And again, if you're approaching 0 from the right, that means you're always plugging in positive numbers. If you're always plugging in positive numbers, can you guys hear me out and that the absolute value then just doesn't need to be there? If you're always plugging in positive numbers? So if we're coming at 0 from the right, always plugging in positive numbers, this is just the same thing as x over x plus x, which is x over 2x, which is a 1/2. Yes? So that was a 1/2. In 10, I'm definitely tempted to change that numerator, x plus 3, x minus 3, and then keeping this part over x minus 3. This is specifically asking me to approach 3 from the left, which is right. So if we think about these as two different functions and look at our limit as x approaches 3 from the left on x plus 3, and look at the limit as x approaches 3 from the left on this function, this one you should recognize. It's a jump function. So that's always either 1 or -1 because it's something over itself. So from the right of 3, you'd be getting a positive over a positive, so it would be +1. From the left of 3, you'd be getting a negative number over a positive version of itself, which would be -1. So this limit, as you're approaching 3 from the left, is -1. This, truthfully, doesn't matter if you're coming at it from the left or the right, because this is just a line. So it's going to be the same regardless of which direction you're coming from. So you can just plug in 3, and what do you get? 6. And 6 times -1 is -6. I'm just going to show you what this graph looks like, just for fun. Math, absolute value, x minus 3. There's definitely something funky happening at 3. Oh, I should go -10 to 10 so I see. So coming at it from the right, it was at +6. Coming at it from the left, it's at -6. Yes? This part is always going to be 1 or -1. This part is going to change based on the plug-in. So that's why it's not a flat line and a flat line, because it's not just this type of function. There's this other thing in there that's messing with your numbers. Josh. Mm-hmm. If it's just like this, yes. But if you flip it vertically, then it's going to flip it upside down. Yeah. So you just have to be careful if there's other stuff going on outside of it. All right. And then 11, 12, and 13, we have to talk about asymptotes. Okay. And we sort of had a loose conversation about this before. Vertical asymptotes. What numbers make this denominator undefined? 1 and -1. So we have 2 vertical asymptotes because of that idea. If x is 1, the denominator is 0. If x is -1 and you take the absolute value of it, your denominator is also going to end up being 0. So we have 2 vertical asymptotes at x equals plus or minus 1. Our horizontal asymptote rule is based on degrees, yes? And this is a same over same situation, correct? No, it does, because it's going to give you 2 horizontal asymptotes. Okay, which that's the part we've loosely talked about before, but we're going to talk about it more. So it is a same over same situation. And so that would be coefficient over coefficient, so a -1 over a -1, which would be at 1. But because of the absolute value, that could be at 1 or at -1. So you actually have 2 horizontal asymptotes when those absolute values are involved. Okay? So if you jump to 12, so let's look at... So this one would be C. Think about what happens as you approach positive infinity. Like if you approach positive infinity for your x, your numerator would be negative infinity, and your denominator would be 1 minus infinity, which would be negative infinity, which would be 1. Yes? You follow that? Because your numerator is approaching negative infinity. Your denominator is pretty much approaching negative infinity also. The 1 is negligible. And so it pretty much is something over itself, which is 1. Versus if you approach negative infinity, negative infinity would make the numerator positive infinity. And then this bottom would still be 1 minus infinity, which would be negative infinity, which would be negative 1. If you think about it from that plug-in standpoint. Number 12 just says how many asymptotes are there. So how many vertical asymptotes do we have? 2 at x equals plus or minus 1. And for the horizontal asymptote, it's same over same. Coefficient is 1 over 1. So that would be at y equals 1. But because that x has absolute values around it, as you go towards one of the infinities, you approach positive 1. As you go toward the other infinity, you approach negative 1. And so you have 2 horizontals and 2 verticals, so the total number of asymptotes is 4. And in 13, again, you have 2 vertical asymptotes, x equals 1 and x equals negative 1, so that's B and C are definitely asymptotes. And your asymptote horizontal rule is same over same, which is 2 over 1. So you've got, but because of the absolute value signs, you've got 1 at positive 2, y equals positive 2, and also 1 at y equals negative 2. So the only one here that's not an asymptote is E. When you have 2 horizontal asymptotes, as you go towards infinity, you're approaching one of those values, and as you go towards negative infinity, you are approaching the alternate one. So that your graph looks something like this. Towards positive infinity, this is going towards positive 1, and towards negative infinity, it's going towards your other horizontal asymptote, which is at negative 1. Okay? I picked out the hardest of the bunch, ones that were more discussion, kind of newer topics. So your entire homework won't be all that deep. I definitely picked out the harder ones, the tougher concepts. So finish that for homework.